Okay. Hello everyone. Let's see if we have everything working. Sound check. 1, 2, 3. Should be good. I'm trying a little bit different layout for this live stream, so we'll see how it goes. Okay, is the audio volume all right? One, two, sound check. 1, 2, 3. So in this video we'll be doing some repairs hopefully, and we'll see how that goes. So in front of me I have let's do it like so for now. I have SIG Keithley 2425 source meter, and this is the same unit which we were troubleshooting some time ago in previous live stream. So the issue is with this digital power supply board, and I got some new parts, reverse engineered piece of schematics for it, and we will try to repair the damaged components, apply some power, see if we can get any progress, and hopefully we'll be able to get some good results. So that's the idea, and I'll be changing some lenses to get a close-up. And for those who didn't watch the previous stream, the issue with this board is there are two MOSFETs that drive this big transformer, and one of them is damaged and cooked the whole PCB around it. So this is the bad MOSFET. I'll show the closer look in a second. So essentially this is the main isolated power supply section that powers everything else on the analog board, which we have sitting here separately, and we'll see. Let me change some lenses. So hopefully you can see like all the damaged part right there. Can use my pen. So this is where the MOSFET was, and I can show you there was a heatsink, and the heatsink supposed to be black like that, but because of all the heat it's turned like this golden color. And the MOSFET itself exploded its guts, and the MOSFET, the part number is International Rectifier IRI 540M. So this is the damaged component. It's nothing special, pretty average MOSFET, but it have the insulated package because those heatsinks are under live voltage to transformer, so they use the isolated package, because actually you can see second MOSFET right on top have the thermal sensor attached to it, So it would detect like if the MOSFET get too hot to shut down the unit and save the damage, but they didn't put the second thermal sensor on the second MOSFET, and I guess we didn't get lucky. Everything else on this board looking okay. This is fairly new board. You can check the date code on the CPU, and it says 2011, week 41, so it's not very old unit. So we will not be doing any capacitor replacements or anything like that. And this large thing under the heatsink is high voltage to 24 volt DC-DC converter from VCore. Fairly expensive part, but we'll see if that is still okay or not, because these two MOSFETs, let's see the on schematics that I drew a little bit before this live stream. So let me zoom in. So we have the MOSFET driver, this 8-pin package. It's ICL interseal, today Renesas ICL 7667, just a 2-channel driver. We have some resistors, some diode, 2 MOSFETs, and then that large transformer. And the middle tap of that transformer is connected to 24 volts from the DC-DC. So by switching those MOSFETs on and off, we can generate the AC waveform on the transformer and use it to provide isolated voltages. And this power supply is designed to provide plus minus 42 volts and plus minus 85 volts for all the analog section on the power supply. So yep, that is essentially whole circuit around the transformer. And the MOSFET that is blown is this Q12. They are exactly identical. So I was using a separate unit 2425 as well to reverse engineer the schematics, because this unit have totally working digital board. I can show you. This is how it's supposed to look like. So this is on the good unit, and you can see the wires for the temperature sensor. They go only to this MOSFET, but not that one. There is a fan nearby. It's a 24 volt fan that is always powered on, and otherwise it's completely the same stuff. And here we can see the actually marking on the chip is slightly different. Let's see if I can get a good light on top of that. You can see it's Interseal logo 7667 CPA, and the driver on the damaged board is actually a little bit different. It is Maxim Max 626 CPA, but functionally it's the same part. So I have bought driver and MOSFET from good old DigiKey. So here we are. I'm not sure if the driver is also dead. This is ICL 7667, but I just bought the driver just in case. And here are the MOSFETs. IRFI 540, exactly same part number as original part. So it's N channel 100 volts, 20 amp isolated package transistor. Okay. So we will have to investigate that mayhem on the PCB a little bit closer and figure out what we need to connect or isolate, because again it's a little bit of a challenge as this PCB is 4 layers, so we have some internal layers to take care of. All right, hopefully the quality of the audio is all good. Okay, there is a audio level, I think. Let me see if I have any settings to improve that situation. I can add some gain, probably. I'm not sure how that will affect noise, because I have quite a number of equipment running around. So I can do a little bit of gain. How about now? 1, 2, 3, sound check. So, and like the reason why I cut the hole out of PCB, like this is how it was looking originally. You can see everything black and charred on the PCB, and the issue is, like, sure, you could take the damaged MOSFET out and put a new one in, but that would be a very quick road to failure, because of the carbonized PCB material is now slightly conductive, so you will have, especially with a high power circuit like this, you will have all the different smokes and sparks, and it wouldn't be good. So we need to restore the PCB isolation properties, and the only way is to remove all the carbon and all the black substrate and replace it with the air wire connections. Probably put some epoxy on top of it for protection in the future. But essentially this is the universal approach what you need to do if you have the hole burned through the board. All right, so this is how it looks now, and we can see the other side. It doesn't actually look too bad. I was expecting worse, but a little bit challenging, as there is this big polygon on the bottom side of PCB and also similar polygon on top side. So we'll need to remove some of that to get access to second and third layer, because this top polygon, it's plus 24 volts, and the bottom, I believe, is ground, so we'll have to check that. All right. Obviously all the connections and traces nearby need to be checked before we install the new MOSFET in there and start restoring the connections. Otherwise, if we have something like 24 volt shorted to ground, then we might kill some other stuff around, and we don't want that to happen. So let me connect camera to the microscope so we can actually get a closer view what's going on. Okay, camera is mounted. It's a little bit sideways for whatever reason. Okay, that's better. Let's see if we can get anything going. Okay. Need to adjust the focus a little bit. No sound. 1, 2. Why no sound? Yeah, the sound should be fine. Okay, so this is what we have on the board. As you can see, there are some pieces of the copper. This is essentially top layer. We have some trace or piece of polygon shining on the bottom layer. It's connected to this hole, which is good, so we can do the connection. We have something sticking out there, but the good part that we don't have any black material around, so this is all nice and isolated. And we still have this one of the pins. It's actually connected to ground on both sides of the circuit, and this is just this black stuff. It's a thin layer of carbon on top surface. Doesn't affect anything. It's quite easy to scrape, so we can clean that a little bit later. But what we need to worry is this is mechanical hole for heatsink, but otherwise it doesn't look very bad. We'll need to figure out what this trace was. Is it the same as that one or not? Because there was, like, remember, pin 1 here, pin 1 there, and we can see on the bottom side here's the bottom. There we go. So this is just we have thermal connection here, here. This is all ground layer, so no need to worry much about that. And I don't see any other metal, so looks pretty good and clean. And we can see some dust and some crap around this 100 ohm resistor. This is most likely a diode. That marking 5D and sideways T. Then we have our driver. Looks physically fine, but I'm not sure if it's dead or still good. And this is the second part with another MOSFET. So that's the situation. So we can take the multimeter, do some probing, and see where this stuff is connected, and if it matches our schematics or not. Okay. So I'll just use Fluke 87 5 DMM in continuity mode, so we can do some probing and see what we get. So this is the schematics. I'll use the drone schematics as the reference. Now we can see the 12 volt. So for 12 volt I'll use this convenient point right here. And this is not 12, 24, I'm sorry. So we can check the connectivity here. We get like 2 ohms something. And let's see what we get here. We get nothing. And this is indeed connected. My probes are not very good. So the question is, what is that? Let's check the ground. So this is the ground pin. Pin number 3. Okay, so there is some capacitance there. And we can check this. So this is the gate. I don't like these probes. Let me try some other ones. Yeah, this is much better. So we have our 24. This is our ground. This is indeed ground, all connected. And I believe this is the transformer then. So there are 2 things we can try. We can just have the temporary connection of the MOSFET to these points and apply a little power and see if we get like some signals, and if it's start to show signs of life. Let me clean the dirt. Or we can go all out and do all the installation with the heatsinks and everything, and hope that it should be good and no other damage, which is not very likely, but possible. Okay, the half zoom level would be like that with a hole, so I mean with a circle due to different lens configuration, but I can leave it like that. So let me clean the area a little bit more. This is just IPA, so we can actually see a little bit better. Still see a little bit of the brown stuff near the trace. There we go. Alright, so we also see a little bit of black here. Let's dig a little bit into that. Where's my trusty blade? X-Acto knife. Okay, just on the surface. I think I'll leave this as it is. There is quite wide insulation around, but definitely this pad was cooked. It doesn't seem to propagate a lot inside, so I'll just leave it as it is. Because the main heat was from the MOSFET and the heatsink was just a collateral damage. Yes, that is heatsink mount pin. Yeah, I think I'll just use the tweezer to scrap the black stuff. The blade is a little bit too sharp for that. I don't want to scrape the mask too much. Just make it a little bit nicer to look. You can see even the solder mask, which is usually white, like you see in like these labels 2420, 2430. Here, like all the seal screen become like browny yellowish. Get a tan from all the heat. So what you guys say? Should we just go for it and prepare for fireworks? think I'll just remove this bit of the copper. And just for fun of it, we can investigate the original transistor. So this is the bastard. We can see that crack where all the guts come out. And the crack, maybe we should hammer it later and see the damage on the chip. That will be fun. Well, maybe later. And we can see the heatsink, like that's where that extra blast and all the deposited material came into. It went all the way through the anodized layer. And one of my lights died. There we go. So let's clean up this hole and that hole so we can mount stuff inside. How's the live stream going? Everything good? Was the gate shorted drain to source? I don't know, let's check. We can check that. Yes, it's 33 ohms and 1.1 ohms to the source and drain, so it's very dead and very shorted. We can check the driver, what's on the output, if it's shorted too or not. Doesn't look like, at least not to ground. Let's see the power supply pin. Yeah. Hard to get there under the microscope. Let me do this off the microscope. Doesn't seem to be shorted, at least. So the question, should we remove the driver and replace it anyways? Or just leave it for now? I mean, I bought 10 MOSFETs, so even if we kill one in process, that's fine. They are not very expensive, so no big deal. We can, of course, check the waveforms once we get something powered up to see how they look like, and we can also compare them with the working unit. So let's get cleaned up and prepare to solder. There's my fume extractor. I love my fume extractor. Make the working on boards so much more pleasant. There was I'm on 600 ohms range, so the resistance was at least higher than that. I would say we just replace the gate driver and not to worry about it. So let's do that. Oh. Off it goes. Doesn't look like it have any holes in it, so chances are it was good. But that's not the way we want to question ourselves. One, two, we are back. Someday I'll have a dedicated proper camera for doing YouTube stuff. But that day is not today. Let's get all these pins out. Get all the PCB pins open, so I like to use the toothpick to push all the excessive solder through on the other side. Just like so. Sorry about the fingers in the way. This is the ground pin. So we have the polygon on the other side. It's harder to hit, so we'll worry about that later. Now that we have most of the solder on the other side, it's much easier to use the solder wick. And it will all come right off. Clean excess flux. We see a decoupling capacitor right there. So looking good. Nice and shiny. Now we can put the new chip in. What we can do is also check these diodes, or whatever they are. Let's see. Okay. It seems like just a diode. It's not a zener. That is good. Let's check that resistor. Should be 511 ohms. It's 475. Okay. How about another one? You cannot see it, but it's right under there and there. Yep, that one is 476. Okay, well, I think that's okay. Alright, let's put our driver. I have only one, so it wasn't very cheap. I think, like, don't remember how much, but it was a few dollars. Use the ESD wristband and bend pins a little. Come on. Now we put it the right orientation. There we go. Now we solder it in. It's not very exciting. I don't apply any extra flux for this work because the flux inside the rosin core solder is already enough. You can see it flows nicely. I'll give a little extra heat to ground pin, so we have a nice solid connection inside, and we're done. Cut the extra from the pins. There we go. Now we clean the mess. Looks okay. Nice and clean. So let's now the tricky part is there is 24-volt line and there is a transformer connection through 24 volts. So, and based on this transformer I can see the windings are pretty large in diameter, so the resistance is quite low there. Maybe I'll use my trusty Keithley 2002 to see the exact resistance between native 24 volts and the one through the transformer, because remember the MOSFET, each of them switches one side or another side of transformer to ground, so we don't want to have wrong connection to wrong rail. Let's do this 0 reference point. Now we can check what's the resistance between the 24 volt point and this point right there. So it's 26 milliohms, and yes, I compensated for my probe resistance because I'm doing 2-wire measurement. So this is 26/28 millivolts, and we can check the transformer. You can barely see. So this is 17 milliohm. That is 0, and this is 0, and this is 20 milliohm. And between here and there we have 0, and between here and there should be also 0. No? How about this? Yes. Okay, so this makes sense. This is 20, 20. Okay. I think this pin was connected to the middle point of the MOSFET, middle pin, and this stuff is connected to the gate. So we can jump wire from here to there, from there to there, and this is just native connection, and we don't need to worry about that. All right. So here's the MOSFET. We will need to, actually, if we bend the pin long enough, we may actually reach to that through hole, and it will make our job easier. Let's try that. So I've got the transistor on the heatsink. So now we can just, I need to remove some of the extra solder. Come on. What happened? Are we live? Everything good? Check, check. 1, 2. One, two, three. There is a challenge, because I think the yeah, the MOSFET pin will not go through that small hole. Maybe it will. Let's try to get it free. Yeah, I think I'll need to add a little bit solder there. There. Okay. It won't be pretty, but should be working just fine. Based on the footprint, that looks like there was some probably snubber capacitor or some similar part in there, but Keithley didn't use it in the final design, so it was just empty space, empty footprint on the PCB. Alright, let's see if the pin goes through. It kinda goes, but not really. It's like super tight. But I think we can push it through. So let's figure out the band radius. There we go. I think I need to actually do this off the microscope so I can see better what's going on. And switch to the normal camera. And I also need to cut the excessive length of other pin. And make sure the heatsink is actually getting positioned right as well. Yeah, that didn't work. Okay, I think I can work with that. Let me check for a second. There is some gear beeping at me. I need to see what's going on there. Because somebody sounds very unhappy there. Okay. Okay, that was resolved. So let's go ahead and solder something in. We're back. So now a little bit equilibristics with this pin. Let's apply some solder there. I think that's fairly decent. It's a little bit crooked. And this is how it looks from the other side. So this is our ground connection. Let's give it nice heat So it's flow all the way through. This is the heatsink pin. And this is our gate. I'm not really a fan how this pin close to the corner. Let me see from the other side. I'll just wiggle it a little bit. Okay. Well. Interesting. There was a mount for that via and from the resistor. So looks like it's terminate directly to that pad. That's interesting. Didn't expect to see that. Let's confirm that. Yes. Okay. Well, I can connect just that to that without touching this. Okay. Easy peasy. I think we can just cut this section and run a wire through. Or we can do just a little air wire from there to here, and all this area we then can close. Yeah, I think that will be a better idea. Because this is all ground, so we need to expose it. Yeah. I think I need something better, or actually I need a better angle. Let's clean up the mess. Now I need to find my copper foil. I had it somewhere. There we are. Ta-da! So we need a little piece of it. We need a little hole in it for our pin. And then we need to chop all the excess. Yeah, hold on. There we go. Just a little bit over there. And a little bit over there. And of course we need a better hole. There we are. Need a little square. Oops. Yep. Don't go. Okay, let's. So solder this stuff in. I think it's good enough. We can put a little insulator on that pin. Just to be sure. It's a little bit big. Let's stretch it. Doesn't quite want to go. There we are. Okay. It's just a thermal shrink. Did the smoke itself or from user error? I think it was just by itself. User said that the unit was working fine, and then the smoke escaped, and then nothing happened, nothing worked. So that's the extent of it. I'm just connecting the wire. I don't need to actually go it all the way through. Just need a nice little connection right there. There is no any high current supposed to go over this wire, so let's pull this up a little. There we go. So there is no need for like heavy gauge or anything. That did quite well. A little bit of how you're doing, but it's connected. And then we can epoxy the hell out of this area if this stuff is working. Let's see what happened from this side. Okay. Let's pull that. It's hard to get there. I'll need to do this without camera. And just to push that pin just a little bit. In. It doesn't go. Let's see what the meter says. $25 milliohms. Looks about right. And yes, it was a blown MOSFET. So I believe we can try it on. Okay, let me change the camera. So we can set up the testing area. Here's our patient. So we need to have mains input over there. Change the overview. There we are. So what we need to connect to do the minimum power on test, we need to have our mains 110 volts input. Then we need our front panel right here. And what else we need? We don't need analog board. And that's it. So we need to have a fan. We can put it right there so we can know that 24 volts is going. So the front panel can be on the side. And we do need the mains plug, which is on the case over there. So let's get it aligned somehow. It's fairly short. You know what? I think we can just put everything in the case, because it will be just easier to do. Let's do that. I think fan was going this way. That's the fan screws. Okay. Let me bolt down the PCB so it's nice and secure. Sometimes the mechanical holes are used for electrical purposes, like a common ground point or something like that. So I think I'll just put all the screws just in case. There we are. We have 1, 2, 3, 4, 5, and that's it. There are just standoffs on the corners. Nothing moving anywhere. Fan is not rigidly mounted, but that's fine. So let's hook up the display. Okay. And then see if we get any smoke. There we are. And we don't need the analog board, which goes on top of that like that. So we'll have it just sitting on the side. All we need to do is to power on and check the voltages to see if they are there. Maybe look at the waveforms. And for the first power on, I'll not just plug into mains. I'll use my AC source, which is that serious looking guy over there on top, Chroma 61604. I love that unit very much. And we can set the power limit. So I actually have good working 2425 right in my stack right there. Under this is 2400, this is 2425. So I can connect the mains from AC source to this unit, so I can measure how much current is actually used by 2425, good one. And then we can program the power limit accordingly. Let's do that. So I need a power cable. And we need to disconnect the power and connect the power from the AC source. There you are. It's a little bit tight because my AC source output is right here, bolted to my bench, or rather taped. So let's see. I'll power it on. So 110 volts. It is on, and we can see the readings in the unit. So right now it's around 33 watts, doing nothing, and current around 0.33 amps. We can power off, power on. So I think if we set the current limit to 0.5 amps, that should be good enough. Like for whatever transient capacitors, chargers, or anything like that. So let's try that on the working unit. Page source, current limit 0.5 amps. Page. Okay, so 0.5 was not enough. We enter protection. Let's try again. 0.8 amps. Nope. So let's try 1 amp. This current source protection is very fast, so nope. Let's try 1.5 amps. So it even if it's very briefly going over the limit, it will immediately shut the output off. Okay, 1.5 works. I can see the unit doing its thing, initializing model 2425, and it's all good. And the steady current is 0.32 amps. So let's try it a couple times. It's all good. Again, it's all good. I think we can leave at this. And now we can connect our patient unit. So I'll use this blue mains jack that goes all over there. Let's connect it. Okay, and I guess we either see smoke or we don't. So let's have the camera angle at better perspective. But we also want to see if the display comes out. I think I can tilt it a little. Should be okay. And well, let's see if something happens. Well, I think it would help if I would press power button. And okay, display is working. Current 0.2 amps. Let's turn off and check if we have any heat. I'm not touching anything yet, but so far I don't see any smoke, so that's a good start. We can try to measure some voltages. So there are a bunch of test points right over there. So we can do that. And let's do DC voltage. That's what we want to measure. Let's do 1 kilovolt range just to be sure. Speed we want to have fast. We don't care about precision really. This is just a power supply. Come on. Okay, this is what? Yeah, I think I'll just change the MPLC a little bit faster so we don't get that dodgy resolution jumps. There we go. Good enough. And now we need to have our ground connection and I'll have one ground connection connected through the crocodile, and then I use the red probe with one hand to poke into stuff, so I don't by accident risk touching live stuff, because 85 volts, it might tickle a little, so we don't want that. So unit is off right now. Okay, I'm sitting next to it, nice and comfortable. Let's see our minus 85 volts. And the power is on. Wow, minus 156. And we tripped the protection. Okay, that's quite a lot. Let's try again. Plus. This is plus 85 volts. Plus 156. Could be because it's unloaded. Essentially, there is no capacitors on the output. There are just bunch of diodes and bunch of inductors. So let's try plus 42 volts. Okay, plus 40. And we can try minus 42. Minus 40. So that is much closer. Plus 85. And well, we can look at the waveforms. Let's do that. Just at least to see how it looks like, and then we can probably do the same test using another good 2425, just to see if it's the same or not. So we can take a look on some waveforms. Let me get my high voltage isolated probe, if I can remember where I put it. If only I can find it. I see my 6 kilovolt probe, but I think we don't need that much. Oh, here it is. There we are. It's Tektronix TMDP0200, 200 MHz high voltage differential probe, 750 volts, peak to peak. Should be good enough. have too much mess on the bench. Okay. I need to reconfigure the scope. Channel 4. I want to have vertical set to, let's say, attenuation. Channel 4. Vertical setup. Manual 750 volts, just in case. I think we also don't need 10 nanosecond resolution. Okay, let's hook it up. The probe comes with like this really huge fluke hooks. They are like insanely big. So I think this would be better view. So what we can do is check the gate voltages. This is minus. Let's see, can I plug this in here? Oh yeah. There we are. All right. Let's see what's going on in here. But so far, no smoke. A little bit concerning higher unloaded voltages, but that might be normal. I'm trying to figure out where to put the camera. There we are. Probably like that. Just in case somebody wants to see me. All right. So let's power on. This probe is actually, the tip is isolated. There is a heat shrink, but there is a metal piece over there not isolated, so we need to be fairly careful. Like that. Pokey there and there. Let's power on. It does trip from time to time. Okay, that's the gate signal on the good MOSFET. We need a little bit higher. Let's measure what's the frequency, scale, bandwidth. Measure frequency, amplitude peak to peak, and frequency. There we are. So the signal is 14 volts peak to peak, frequency 60 kilohertz. Looks not bad. Let's try the second channel. So that was where the good MOSFET. This is where the bad was. Okay, looks decent. Ideally, if we would connect two probes to the high, to the first and second, we would see the pulses going to be opposite in phase. So what we can do is now we can look at the output voltage and see what's the ripple and what's the stability there. So this is our 85 volts. Let me get a good connection somehow. Oops. And let's go 100 volts per division. Let's do 50 volts per division. This is minus 85, so we should go down around minus 150 volts. So that should be like 3 divisions. Let's go. Okay, looks fairly stable. And then protection kicked in. I don't see any crazy AC ripple or anything. So peak to peak around, well, 7 volts, but this is low resolution. So let's see, amplitude RMS 154 volts, and we can look at the positive. Positive 157. I think it's okay. We can do positive minus 42 volts. That's minus 40. Looks okay. And that is plus 40. Also looks okay. I think it's working. So what we can do is get the analog board connected. What do you guys say? I think I'll need to bolt down the fan. So far it's a good start. So not too bad for now. You can see the all the shrapnel and pieces and smoke was hitting this metal plate. So this is the analog board. The bottom board is pretty close to 2400 series. They have bigger relays in here, and this top PCB have all the capacitors, like a whole bunch of them, and big Dale shunts for 3 amp 100 watt output. And there is also a big VCS metal foil shunt. So that's how the guts of 2425 analog board looks like. So let's get it all situated in the unit. Like so. Something is in the way. Okay. Quite like the modular design of 2400 series instruments. So like you don't need to mess too much to take it apart. It's kind of crooked now that I look at it. Okay, well. There's the front panel. Oh, that cable. That cable goes right there. So I guess all those high voltage rails, they charge these caps, and each of these cap is 160 volts. They are 160 volts, 220 microfarads. Okay, it's all connected. Oh, okay. The standoffs. Those are from the rear. Okay. Well, it's because of the legs. Yeah, probably. Let's hook up the display board. Connect the terminals. Actually, this one. We need to connect the LED first. There we are. Now the LO, high sense, and the low sense. Now we get the stuff positioned. There's the power button. Come on. Yep. There we go. It's a newer Tektronix unit, so it have white instead of beige front panel, and dark gray for plastic parts. Looks really nice. So I was really surprised that this unit blew up. Like, my 2400 is working 24/7 most of the time of the year, never turn off, and still fine. So go figure. All right, so let's connect the power and see if we get anything out of it. Probably I should put the camera down so we can see display better. Whoop. Whoop. Should be okay. One, two, 1, 2. Sound check. Is anybody still watching this stuff? Or everybody asleep? There we go. We got some focus. Safety glasses, huh? That's a good idea. In case those cabs decide to go big bada boom, it will be a lot of pieces flying around. So that's a good point. So we can put a protective cover on top of it. I just found one suitable enough. So we can do like so. Huh? I got everything covered. Okay, enough joking around. Let's power it on. Okay. Here some relays, click. Error code 601, okay. 10 volts, output on. 10 volts, yay! Now, of course, maybe it's fake 10 volts. Let's do voltage source. Let's hook up our bench DMM and see what we get. So the last calibration was 2013, actually 12, and due is 2013, count 1, so this is just factory calibration for the unit. Display is nice. Let's turn annoying beeps. Beeper, disable, thank you very much. Okay, so it's eating about 300 milliamps, 31 watt, so about the same as my good unit. And I believe we can hook it up to DMM and see what it's doing. So I need to reposition stuff a little. That's good enough. We can see the display and the meter. So this is our so now even the output is off. Let me move the camera around. There we are. Even the output is off. You don't want to be touching output terminals just in case there is some fault and there is actually live voltage there, which can be quite high. So I'll avoid touching exposed metal when plug it in, just a safety precaution. But so far so good. We have 0 volts. Let's output 10 volts. Yep, we get our 10 volts there. I'm not sure if you can see on the camera. Hopefully you can see. Or cannot see. So it's 10 volts, fairly stable. Let's try higher. 20 volts. Okay, we got 20 volts. Let's do 50. 50 is okay. Let's do 100. 105 actually. And we have hit the compliance limit because 10 mega ohm input divider, so we can do 1 milliamp. That should be enough. No? 10 milliamps. It shouldn't draw that much of a current. Oh, yeah, stupid me. Need to increase the range here. So yeah, that is correct. Eating about 10 microamps into 100 volt. 105. Let's try negative voltage. Minus 105. It's fine. We can reduce the range on 2002. So looks pretty good, even not too far off. Let's source some currents. Turn off, turn on. No problem. Let's source some current. So we can do 100 microamps. PCI. There is some offset. 100 microamp, compliance 2 volts. Okay, 100 microamps, almost spot on. We can do negative current. Okay, no problem. We can do 1 milliamp. It's a little bit off. There we go, 1 milliamp. burden voltage around 117 millivolts for Keithley 2002, and readout spot on 1 milliamp. Looks pretty good. Negative, no problem. Let's try higher. 10. 10.5 is the maximum on the range, so 10. 10 is fine. Negative. It's okay. Let's do 1 amp. 1.05, and we hit the compliance voltage. That's okay. 6 volts. Okay. Let's see, measurement. Doesn't seem to want to go to 1 amp. Huh. Okay, now we got 1 amp. It was just the same thing with the, because SMU, like 2400 series, they have measurement range and then they have source range. So if you have the source range, even can set on higher output. If you don't switch the measurement range, it will be clipping the output to the limit from the lower denominator. So yeah, 1 amp we have no issues. Minus 1 amp also fine. So what we can do is to do the self-test. So how you would do the self-test? If you just go and it's normal, you would see in the, I will go menu, test, you only see display test, so you cannot do any functional tests. And display test just shows like what keys you press, display patterns, nice and uniform VFD. So let me show you closer. There you are. All the different characters. That's all good and dandy. What else? Char set. Blah blah blah. Oh, it's a lot of charts. Okay, but how do you test actually functional issues? Well, you need to enter the secret mode, press up and sweep, power the meter on, keep buttons holding, keep holding. Now you can release. Reading buffer data lost. Go disable the pesky beeper. Now we get a extra secret menu, which allow you to change the model number. Either go all the way different, but don't do this, because if you change the model number, then and save, then all the calibration data will be lost. So that's not what you want to mess with. There is a reason why these settings are hidden in the secret menu. Then there is a front panel burn-in. It just highlights all the sectors and all the elements on the display to make it more uniform. That actually didn't work for all the units. I tried, like waited for many days. You can also change the analog revision board and digital revision board, and also enable or disable contact check function, but I believe that needs some hardware on the board. But that's all fun. What we really care about is that if we go general menu, main menu test, now we have built-in test enabled. And the reason why they hide built-in test is when the SMU is going through self-test, in these modes, it can output high voltages and dangerous voltages on the output terminals. So if somebody touches the terminals during the self-test, you can get problems. So I believe this is the reason why they hide it under the secret mode. So let's go built-in test, do the automatic test, and do the full test. Continuous repeat, no, we don't need that. And it asks you what to do. So we have the front panel terminal connected, so it's asking you to insert 4-wire short. We have one of those. So there is 4-wire short, it just connects all the wires together in a star manner. So we plug this in and press enter. Now the meter will run through the different test steps, and if there is any error, there will be a star in here or a snowflake. So that is the my AC source kicking in protection. My bad. I'll change the setting to slightly higher. Let's do maybe 3 amps. Output on. Oh. Now I need to enable the secret menu again. The main part I don't really like about 2425 is fan. So it's always working on the almost max speed. So there is no mode when it's off, and it's kind of annoying. 24-volt fan. So that's I prefer, like if I need to do any small power test, I always use 2400 instead of 2425. So let's go again. General, beeper, disable, built-in test, automatic, full, continuous repeat, no. We have front terminals, and let's and of course on the most interesting part, my battery in the camera dies, but so far it's going. I'll run it again in a second. So far so good. Ten amp range, clamps. Test complete. There is no issues. So that's a good, easy repair, I believe. Let's do it again. So you don't say like, oh, you cheated and swapped the meter with another one when the camera was off. Running again. It's quite elaborate actually self-test, and a lot of different points, which kind of makes sense because this is quite sophisticated instrument. Have quite a lot of stuff going on inside. It have the sweep capabilities, protection, different limits, all the nice programmable current sources. Test complete. We can check the readings. This is ADC reference readouts. Deck zeros, voltage deck, different signal levels, voltage clamps, feedback, noise. I believe we go back from the first. Yep. So there we go. The rest I'll have to remove the analog board again to get the epoxy on the digital board in the damaged area. Then obviously I'll need to check everything else to make sure it's all good. And by saying that I mean like measuring the output voltages, noise, currents, and the epoxy is actually almost like a solder mask. Oh, my current source tripped again. Probably it's catching some transients. So 3 amps, let's do 5 amps. Or we can do all the way to 16 amps, and if something catches fire, then this will be a good moment to do. So this is the epoxy I'll use. This is actually a solder mask. It's kind of like a gel. It's like slowly moving, and then with the ultraviolet light, it's cures. So it will almost look like a PCB material in there, nice and green. Let's do the self-test stuff again. Test. Oh. Test, built-in test, automatic. We still can do another video showing the calibration of it if you guys want. So just let me know in the comments if anybody wants to see the calibration of 2425. It would be mostly automatic, but I think 10 amp range I'll have to do some more elaborate testing. So let me know if anybody wants to see the calibration of this unit. And obviously I'll need to put all the parts, like the handles, that's the filters that sit on the cables, all the legs all together, have it warm up couple days, and then we can do the calibration stuff. Probably next weekend, that would be a good time. Overall, I'm quite happy how this turned out, because the alternative was to replace the digital board, and I don't think that would be any less than a couple $1,000, given that most of the manufacturers nowadays they don't do component level repairs. They just, oh, like, sure, we can replace the whole board for you for 80% price of the instrument. So sadly, this is more common situation, that it's easier to scrap the unit, and cheaper also, than trying to go do actual repair. So I do hope that situation may be improve in future, but well, all I can do is to show repairs like this on my YouTube channel and also on xdev.com website. So more engineers and people around tinkering around electronics would be interested and actually know that such repairs can be fairly easy, and they could do a lot of fun projects without spending tens of thousands of dollars for replacement and new instruments every time. So essentially, if I can show somebody by doing this in example, well, that's a win for me. Obviously, it have to be interesting for me as well, so I wouldn't be bothering repair some cheap handheld DMM because it's just not what I'm interested in. So that's why you mostly see this obscure, high-end, expensive equipment on my channel. Well, just only so much hours I can spend on electronics hobby. So it's running self-tests over and over and doesn't seem to have any issues. So I'd say it's a good repair and good result so far. Okay, if any questions, I'll still be live for a couple minutes. Sadly, 80% of interesting stuff is listed in the US. Well, yes, but it depends on dedication. Sometimes you can find stuff in other geography and countries, and most of the equipment I have, which is quite a bit by now, is purchased, broken, and shipped from US to Taiwan, because I was living in Taiwan for almost 9 years, since 2011. And yes, expensive shipping for every item. Like sometimes I buy a little MOSFET, like the ones I showed earlier, and the one that we used to repair this unit. So the MOSFET price was like $5 and the shipping for it was like $30. So yeah, I probably spend like 30 or 40% of money on this hobby just on shipping alone. And again, like if you're patient, then sometimes you get these instruments for a very decent price. So yeah, sometimes it's have to wait for a year or two before something pops up for a decent price. But it's not like, oh, like there is a business plan and we need to have this instrument by tomorrow. So it's okay. Every piece of equipment I get, I try to document and publish an article about it on xdevs.com, including repair, calibration, or whatever may be involved in the project. Sadly, I don't have everything there, but most of the stuff I try to keep up. And if I have updates, then I often update the previous articles. So just for the 3458A, we have like maybe like 5 or 6 articles already covering different units, different repairs, stuff like that. Also a good community is on EV blog forum in metrology and repair section. So you can find many enthusiasts who are doing different repairs and experiments and measurements, all the fun stuff. All right. So I believe that's it for now. And I have actually second 2425, which have good digital board, So I can show the unit right here. So this is older instrument. It have good digital board, a good power supply, but have issues with analog board. So it have some self-test errors, and outputs are not correct. So this is the analog board without the top board, by the way. It's an older instrument. This is around a year. Let's see some date codes. This is a 1994 board. So have a lot of resistors standing up, some temperature sensor, all the good stuff. So this will be a repair for some other time, maybe not even live, because like we already see 24, 25. I'm not sure it will be much interesting to do many videos about the same instrument, because I have more interesting, exciting things. So I believe that's pretty much a wrap. And next video I think will be about something more exciting than SMU repair. So that's how the bench currently looks like, with all the stuff on it. And we have another one over there. If I can get some light over there. There we go. So somebody may spot some of the resistance metrology equipment. So we'll be doing some resistance stuff. All right. Well, that's a good video for today. And any comments, any feedback is very welcome in comments in either this video, or you can always contact me on xdevs.com website. Just go xdevs.com, click about, and then you will find all the contact information, how to reach me. And thank you everyone for watching. Bye now.